Okay, I want to pick up this video right where we left off the last one, and I want to begin talking about outliers. We've talked about measures of center, we've talked about measures of spread, and measures of spread allowed us to determine where things are expected, where observations are expected, and it's based on the shape of the distribution. We talked about measures of relative standing, and the last topic I covered was z-scores. And a z-score measures how many standard deviations an observation falls from the mean. And so when we talk about outliers, we're talking about the observations that fall outside where we expect them to fall, the ones that we don't expect to see. Now, the way that we set this up is based upon where we've been. We said in symmetric and skewed distributions. Remember, symmetric, let me go ahead and get a pointer here because I'm always like my pen. Symmetric distributions, we'd be using the empirical rule. Skewed distributions, we'd be using what we call the modified empirical rule. But regardless of which of those we're expecting or looking at, we're expecting observations to fall within two standard deviations. And so we're going to go and say those that fall outside two standard deviations are not expected. Those are going to be called outliers. And the only thing that changes when we move from the symmetric or the skewed distribution to when we're working with Chebyshev is we don't know the shape, so we have to hedge our bets a little bit and go outside x bar plus or minus 3s. Now I could just as easily say mu plus or minus 2 sigma, mu plus or minus 3 sigma. And you can see that I use these symbols kind of interchangeably as we go. It doesn't matter if you're talking about populations or samples. The idea stays the same. All right, we're going to say that outliers indicate one of the following problems. So if you find an outlier, one of three things has got to be true. One, the observation may be miscoded. Years ago, I used to collect survey data by taking a survey in class, and I would ask students to give me answers to various questions, and then I would take the answers they gave me home, and I would enter them by hand. Well, with a large number of students, it took a long time to enter it, so I got really fast at entering data. But by going really fast, there was also the chance that I may have messed up. And I remember one semester, I asked the age of students, and when I looked at the data set that I had entered, I had a student who was 222 years old. And I thought to myself, wow, that's an old student. I don't remember seeing any. They must have looked good because I didn't notice anybody that old. And of course, I'm joking because I miscoded. The student was really 22 years old, and I had hit the 2 a third time and entered it as 222. Now that observation showed up as being unexpected. It fell outside where we expect the student's ages to fall because it was miscoded. And you'll see this from time to time. Occasionally you have an extra 0 on your data set, or maybe a misplaced decimal point. Think about it, your GPAs, if you forgot to put the decimal point in, instead of like a 3.2, all of a sudden you have a 32 GPA. Then it's miscoded. It's an outlier because of it being miscoded. All right, second one, the observation comes from a population different than the one specified or the one that you think you're using. Occasionally with real estate data, you get a home and you look at the sales price of a home and you're like, wow, that's huge. It usually happens because the house price is really, really large. And usually, well, I shouldn't say usually, sometimes when you're doing that, it's because it doesn't really come from the area you thought. I remember once a student was working with homes over in Pinellas County, and they got a home. Most of the homes were in like the $300,000 range, $200,000 to $400,000, let's say. And one of the houses was like $3.2 million. And at first it was like, well, he just probably put an extra 0 on it, but that wasn't the case. It was $3.2 million. And then when they looked a little closer, it's because the house that they were working with actually was on the Gulf of Mexico. It was a couple of streets, maybe half a mile from the neighborhood they thought they were working in, but because it came from a half mile in a specific direction, and that direction landed you on the Gulf of Mexico, the home price was a lot higher, which you can imagine it would be. But that observation came from a population of homes different than the one the student thought they were working with. And so that could be a reason. And then thirdly, the observation is a result of what we're going to say rare chance. And I'll use this word loosely here. If you think back to the way we just defined outliers, we said outside x bar plus or minus 2s in mound-shaped distributions, outside plus or minus 3s when we're using Chebyshev. And think about those rules. The empirical rule says 95% fall within 2. The modified empirical rule says somewhere between 90 and 100% fall within 2. Chebyshev says at least 89% fall within 3 standard deviations. And so there's going to be a certain percentage of the data that falls out there, that falls further out, further than 2 or further than 3 standard deviations. And so those are the ones we're calling outliers. a rare chance. And depending on which data set you're working with, it could be as much as 10 or 11%. So I'm using the word rare, but I'm using it loosely. All right, so that's the outlier. That's defining outliers. My dog is having a little fit in the background, so I hope you stop. Her name is Rain. Hey, Rain. Rain. Shh. Sorry about that, folks. All right, so here's how I want you to think about it. There's your little outlier. Usually you don't hear dog noises in my videos. Chip example. When I do this lecture live, I bring my poker chips, and you guys probably all remember my poker chips from the first day of class. They're in that little plastic bucket, and in this bin of chips, 95% of the chips are red and 5% are white. Okay, so I set up an empirical rule. And so I think I actually have that in your notes here. I do. 95% are red, 5% are white. And so you can think of this as being an empirical rule population. Within 2 standard deviations would be 95% of your observations. Outside of 2 standard deviations would be 5%. So I set it up. And what I try to show students, or what I try to explain to students, is that if you were to randomly pick a chip, while you could see a white one, it's possible to see a white chip, it's very likely that you're going to get a red chip. And I tell my students, and this is a true story, I tell my students that I've been doing this chip example for years and years and years and years. At last count, I was approaching 250 times, because I do it in every section, every semester, and let's face it, I'm getting old. So 250 times, the chip examples really only failed me twice. And so I'm amazingly ahead of the game in terms of what's expected. So anyway, I set this up, and then rather than pick the chip myself, which students would tend to doubt that I would do it fairly, I let them pick it. So I had to imagine, if you will, I have this bucket of chips, and I'm just kind of shaking them to mix them up, and I go to a student in the front row, and I say, all right, now please pick a chip. Just reach in without looking and pull out one chip. And I set it up in such a way, it's not going to translate on this video, I'm sure, but I set it up in such a way so everyone's expecting the red chip. And darn it all, don't you know what happens? A student reaches in, and they pull out a white chip. Now, typically what happens when that happens is the class kind of laughs. They think that's funny. There's this joint mentality of, hey, we got you. You were expecting a red one. We got a white one. Ha, ha, ha. And it's pretty funny. And I kind of laugh it off and say, well, there you go. What are you going to do about that? And so I go to my next student, and I have he or she reach in, and darn it all, don't you know, they pick out a white one too. And it's at this point in time, one of two things happens. Either students laugh louder, which happens from time to time. They're like, oh, wow, we got you twice now. Holy cow. Or students start to raise an eyebrow. And then I go to a third student, and again, a white chip is selected. And it's at this point that almost everybody in the class starts to begin suspecting that perhaps I've lied to them. And they usually don't call me a liar. They usually say something like, oh, wait a second, this is weird. What's going on? Are you sure you got the right chips? Now, what's funny for me is that occasionally after that third white chip is selected, there's a student who laughs even louder. And it's funny because every now and then, every semester, there's usually one student who I could pull out 100 white chips in a row. Just reaching in, pulling out a white chip, and they'd be laughing. They'd be like, wow, that's funny. And they would laugh louder and louder and louder and louder, and they would never really get my point. As you begin to see these white chips after white chips after white chips, at some point, we expect a red. At some point, you got to start saying, wait a second. And so we pick, let's say, I'm just going to use a W, white, 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 and on and on and on and on and on it goes. Occasionally a red chip will come out. But most often not, it's white chip after white chip after white chip. And at some point, you got to say, wait a second. Now, here's the problem we have with this. I want you to say, wait a second, right there. And while you're watching this video and you hear me talk about it, you're probably thinking, oh, I would have done it. I guarantee you wouldn't have. Nobody ever says after the first one, wow, you're lying. And that's when you need to, because a chip, in the context of this example, a chip represents a sample for us later on. We only get one sample. We get one look at the population. If it's what we expect, if you pull a red chip out, you're done with it. You just move on. If you pull a white chip, you say, hold on, I don't believe it. I don't believe the population is as specified. And that's an uncomfortable thing for students to do. it's uncomfortable for everybody. I shouldn't just limit it to students, because very rarely will you run into somebody who, when they see that contradictory chip, that contradictory information, will they challenge the population or the person that's telling them the population. Why this is important, it helps us talk about outliers now, and when I get to do it in class, it's a fun little example. But where it's really important for us is later on when we talk about the test hypothesis topic. The test hypothesis topic is a pretty straightforward idea, but unfortunately we layer it with a whole lot of symbols and terminology and what I technically refer to as crap. And so I put a whole bunch of junk on top of it, and it gets tough to remember that it's a pretty easy idea. And so when we get to the test the hypothesis topic, I'll say, all right, hold on, let's take a time out. It's a little, I can tell when I look at students, I can tell when it's a little challenging or something's not right. I say, think back to when we talked about the chips. Remember, we had 95% of them were red. We reached in, we pulled out a white chip. At this point, you'd call me a liar. That's basically what we're doing. The terminology we'll use, because I know some of you guys have seen some of this before, the terminology that we'll use in test hypothesis is we won't say the population is lying or Mark is lying. We're going to say reject the null hypothesis, because a null hypothesis is going to be what specifies what's expected. And so you may remember saying things like at alpha equal 0.05, we reject H naught. If you do, that's where I'm heading. If you don't, if you're like, oh my gosh, I've never heard that before, don't worry about it. We'll get there. That's chapter, that's later in the book. I don't even know what chapter it is. But we'll get there when we do the inferential work. So anyway, that's my chip example. It's worth talking through, even though you're not going to get a chance to see it live. All right, so we talked about what an outlier is. I give you a little example. How do we detect it? Well, there's two methods. One should make complete sense. This one, the z-score method. Use the z-score for an observation and the shape of the distribution that it comes from. And this piece here, the shape of the distribution that it comes from, you may not even need to consider that to determine if an observation is an outlier. Okay, if you're following along everything we've done here in chapter 2, you understand measures of center, you understand measures of spread. We have these rules that tell us what's expected, what's not expected. If it's not expected, we call it an outlier. Well, rather than looking at mu plus or minus sigma, mu plus or minus 2 sigma, mu plus or minus 3 sigma, we can just take a look at the z-scores. Because mu plus or minus sigma we saw a little while ago, that could be the z-score plus or minus 1. Then you move out to plus or minus 2, plus or minus 3. So if I tell you have a z-score of 4, that's going to be an outlier. And I'll give you some examples in just a second. So that's the z-score method. The second method is referred to as the box plot method. This is a graphical display that utilizes the quartiles of the data set as the basis for determining outliers. Notice what I didn't say. I didn't say the quartiles identify the outliers, but they are the basis for determining outliers. One of the key differences between the z-scores and the box plots is how the outliers are identified. And if we remember the z-scores, let's see if my pen will work nicely for me here. We're going to take a value of x, we're going to subtract off the mean, and then we're going to divide by the standard deviation. I'm going to use an S. That looks like a 5, but that's an S. As I'm doing these notes, I'm working with a mouse. It's not always pretty. So X is an individual observation. X bar, as we've already talked about in a earlier video, X bar is the mean, and it can be influenced by the outliers that we're trying to detect. So if you have a very skewed distribution, the outliers are drawing the mean towards them. They're also making the standard deviation bigger. So both the mean and the standard deviation are affected by the outliers that we're trying to identify here. With the box plot, we're looking at the quartiles. Remember, the quartiles are the 25th and the 75th observations. They're not affected so much by the outliers. It's very rare you'd have 25% of your data being outliers. And so if you take a look at the quartiles, the way the box plot's actually put together is you look at the difference between the difference between the quartiles, and you get what's called the interquartile range. This range between the quartiles, there's some multipliers that come up with some ways of identifying outliers. And usually you go 1.5 or 3 times that interquartile range above and below the quartiles. Bottom line is the quartiles, the 75th and the 25th, where most of your data falls, half your data falls in between there. That's what's being used to identify outliers. So sometimes we think of the box plot method as being a little bit more sensitive. It's not influenced like the z-score method is. So let me give you examples of how we're going to use these things. So let's go and talk first about the z-score method. As I mentioned a little while ago, if you have a z-score of 4, that's obviously going to be an outlier. Where it gets a little tricky is what about other numbers? Now, sometimes people will just say use a z-score of plus or minus 3. If you get z-scores that are outside plus or minus 3, we'll call those outliers. And that's a pretty good rule of thumb. However, what we've looked at in this last section of the course here is we've looked at the shape of the distribution and how it plays a role in where data falls. And we've specifically looked at 3. Remember, I gave you a third one. Usually you think about Chebyshev and the empirical rule, but I also added the modified empirical rule. For purposes of this discussion, you can consider the empirical and the modified empirical rule to be thought of the same way. What we learned is that even when there's skewness, we still expect to see things fall within 2 standard deviations of the mean. When we don't have a symmetric distribution or a mound-shaped skewed distribution, mound-shaped symmetric, generally mound-shaped we'll say, we have to rely on Chebyshev, and that's where we said we expect most to fall within 3. And that's typically where people use that plus or minus 3. If data fall within 3 standard deviations of the mean, the z-score is going to be plus or minus 3. It's going to fall inside of that. And so when you're working with Chebyshev, that's the number we're going to compare. So z-score 1.2, not an outlier. A z-score of negative 2.2, that observation falls 2.2 standard deviations below the mean. It falls inside of 3. No. Here's your outlier. This observation falls 3.2 standard deviations above the mean. That falls more than 3 standard deviations above the mean. That would be called an outlier. So what about, let's go to this one. What if I'm working with the empirical rule? What if I have a mound-shaped symmetric distribution? Notice I'm changing my rule now. I'm going from Chebyshev to the empirical rule. As we saw earlier, our percentages change greatly. So this observation falls 1.5 standard deviations below the mean. Well, in the empirical rule, we expect things to fall within 2 standard deviations. This one meets that criteria. It falls within 2. It's considered an outlier. I'm going to skip down here. 3.5 standard deviations above the mean. That's outside the plus or minus 3. That'd be considered an outlier. So anytime you're, let's say, less than 2, we're going to say it's not an outlier, and we saw that. Let's see if I can get my pen. Where is my cursor? I kind of lose it when I go from one screen to the next. That's less than 2. This is, and we can be either positive or negative. That's a z-score less than 2, negative 2. Those are not outliers. When your z-scores are outside of 3, I'll do it this way. It's a little bit easier for me with my cursor. Those will definitely be considered outliers. Where it gets tricky is what about between 2 and 3? What about these guys right here? The negative 2.2, not an outlier. No. The negative 2.5, yes, I'm going to say that's an outlier. I want you to consider that an outlier. Why? Because when I'm working with the empirical or the modified empirical rule, by the way, we expect most things to fall within 2 standard deviations. This guy doesn't. This falls 2.5 below, but it could be a positive 2.5 as well. And so when working with the z-score method, you have to take your time. If it's, like I said, if the z-score is less than 2, greater than negative 2, if it's between 2 and negative 2, let's just say it that way, then we're going to say, no, I'm saying that wrong. If the z-score is less than 2, whether it's a positive or negative number, so 1.2, 1.8, negative 1.4, negative 1.6, those are not outliers. If it's greater than 3, 3.2, 3.5, negative 3.7, 4, 18, anything outside of the plus or minus 3 would definitely be considered an outlier. So when it's between 2 and 3, that's where you need to consider the shape. If you're using the empirical or the modified empirical rule, that 2.5, that negative 2.8, that 2.4, those would be considered outliers. If you're using Chebyshev, it would not. You got to consider the source of the data, the shape of the data. And we looked at ways of determining shapes using some graphs. So that's the z-score method. Pretty straightforward. And as I mentioned, it kind of follows from everything we've done when we started taking a look at shapes of data and means and standard deviations, and it all kind of flows to this point. The z-score method makes complete sense. The box plot method's a little bit different, and there I'm going to just require you, let's see if I can move it with my cursor, we're going to let Excel or some other software program generate a box plot, and then you just got to identify, and it's usually really simple. Some software programs use different symbols. Excel doesn't. Excel just uses a single symbol, just a blue dot or a dot. It doesn't necessarily have to be blue, I guess. But the dot indicates you have outliers. So here, this is working with the number of personal vehicles that cross different border points in the United States. And you can see there are 3 border crossings that have a lot more vehicles crossing than the rest. So we have 3 outliers. Very skewed distribution. I'd say this is skewed to the right. And this is where the z-score technique, because of the skewness, it may miss some, although these are pretty far out there. But we're going to identify 3 outliers. Very easy to see them.
on the plot. Now, some other software programs will give you different plotting symbols, and they'll have different terminologies. For us this semester, let's just think about outliers or not outliers. Let's keep it simple. For other software programs, however, you'll see different symbols, and sometimes the terminology outliers and suspect outliers, kind of sort of outliers. One of the things that's tricky with this topic, when you have those two different plotting symbols, not every software program uses the same one. In fact, I've seen some that use O's and asterisks, and one of them uses the O's as the outliers and the asterisks as the suspect outliers, and the other one switches it around. So Excel just says, you know what, let's identify the suspect, or the ones that are pretty far out there. We're going to call them outliers, and that's how I want you guys to look at it. So this particular plot has 3 outliers. The next one here, what do I have? 1, 2, 3, 4, 5, 6, 7. It looks like 8 different outliers. This is where I asked a group of students to tell me how many hours they exercise per week. And in this particular group of students, I have one student who said they exercise 40 hours per week. That's this guy way out here. And then I had a 30, and you can see, what do I got here? Like 20, what's that? About 27, 26, 25, 24, looks like 21, 20. Those, everything from this point out would be considered an outlier. And actually, you see this little line right here? That's what I was talking about earlier. That's when you take the quartiles, the difference between the quartiles, and you multiply by, I believe, the way this plot's working, it looks like it's about 1.5. This distance, this is the upper quartile. This is the lower quartile. Half your data falls in between there. And if I took about, looks about 1.5 of that distance, and I should be, this line here should be a little bit lower there. 1.5, that distance gets you here. Anything beyond 1.5 interquartile ranges above the upper quartile would be considered an outlier. There's no observations. You can't have an observation that's negative in this case. I'll also point out to you that we have a line here. You can see this line in the background. That's the median. And this value of x right here, that's going to be the value of the mean. And so you see the mean, the box plot actually shows you the mean, the median. It actually gives you a good 5-number summary, a term I haven't used as of yet. Sometimes the minimum, or the smallest value, which would be 0 in this case, the largest value, which we see 40, the quartiles, which you can see the upper quartile right here, the lower quartile right there, and the median. Those 5 numbers are sometimes referred to as a 5-number summary, and you can see them all when you look at a box plot. So if presented with a box plot, you need to be able to tell me how many outliers are. It's pretty straightforward. You should be also able to tell me the shape, or where the mean and the median are. So there's lots of information you can get from the box plot in addition to being able to identify outliers. All right, last slide. So what I did is I took that student data, there we go, and I looked at 3 different variables, quantitative variables. I looked at the age of the student, I looked at the GPA, I asked what's your GPA, and I asked what's your exercise time, how many hours do you exercise per week, and here are the different summary values for those observations. If I remember correctly, I had about 200 and a little less than 250, and they didn't all give me. I had 247 students who told me their age. I had 242 who told me their GPA. I had 243 who told me their exercise times. You can see the minimum, the maximum, the median, the quartiles. I had to use the quartile function in Excel, but I was able to generate that. So I put all those values in one little chart here, and you can see I have some of them highlighted in red. And so what I wanted to do here at the end of this section is just kind of go through some of the things we've talked about: measures of center, measures of spread, different ideas that we've talked about. So you see the age, these of 20.377, the average age, or the mean age. The average age of my 247 students was 20.377 years old. It's the average of the sample data, and I always want you to talk to me or make statements in the words of the problem. Worst thing you can do for me is if I ask you to interpret a mean, and you'd look at this printout and say, well, the mean's 20.377. You didn't add any value. That's what the printout tells me. Tell me what that means relative to the words. And in this case, the average age of the 247 students is 20.377 years old. Look at the median GPA. Again, if you tell me the median is 3.325, you haven't given me anything. The printout gave me that. What's the median tell me? The halfway point, right? Half of the sampled GPAs, half of the 242 GPAs, and I'm getting that from the count down in the lower part of this printout here, half of the GPAs sampled were less than 3.325. The other half were greater than 3.325. How about the mode? See the mode of 5. We don't use the mode all that often, but the most common exercise time, the most frequently occurring exercise time of my 243 students was 5 hours per week. First quartile, down here towards the bottom, the 25% of the GPAs, of the sampled GPAs, fell less than 2.8875, or you could say 75% of the sampled GPAs fell above 2.8875. Now, I don't have this one in red, but you can do the same thing with the third quartile. 75% of the sample GPAs fell below 3.66. 25% of the sample GPAs fell above 3.66. If I gave you the 90th percentile, 90% of the observations fell below that point, 10% fell above. That's how percentiles, that's how quartiles work. You can see apparently I can't spell the word quartile all that well when I created my little sheet here. Last one's a little bit trickier, a little bit more difficult, interpreting a standard deviation. Again, a standard deviation is equal to 6 doesn't mean anything. You need to tell me, you need to use the standard deviation. It's how we interpret them. We need to use the standard deviation to tell me where you expect most of the values to fall. I expect most of the exercise times to fall. And now when you look at it and try to interpret the standard deviation, you have to do it relative to the mean. We expect most of the exercise times to fall. And the answer is going to be either within 2 or 3 standard deviations of the mean. And the way you know which one is which, whether we use 2 or 3, is this shape. I'm going to tell you that the exercise times are skewed to the right. We've seen that, I think, in some plots we looked at. We saw that with the box plot for sure. So the exercise times are skewed to the right. We're going to use the modified empirical rule. When you use the modified empirical rule, we expect most of the observations to fall within 2. So I'm going to go 2 standard deviations. I'm going to take the standard deviation multiplied by 2, and let's see, that's 12. And then I'm going to take the mean, and I'm going to round here because I'm writing with a mouse, and I'm going to say I expect most of the exercise times to fall within 2 standard deviations of the mean. So between 8.03, if I wasn't rounding, plus or minus 12. Now you can't get a negative exercise time. Oh boy, I wish I could get time by not doing anything, or get exercise by not doing anything, but the lowest exercise time will be 0. So I'm going to say I expect most of the exercise times to fall between 0 and 20, and again, if I wasn't rounding, 20.03 hours per week. And that's how I want you to interpret the standard deviation. I expect most of the GPAs to fall between, again, GPAs are fairly symmetric, maybe a little skewed, but fairly symmetric. So you're either using the empirical or the modified empirical rule. So I'm going to take this number, which is slightly less than 0.5. I'm going to take that, I'm going to multiply it by 2, and I'm going to add and subtract it to this. Again, you're going to get a number, in this case, above 4.0, which you can't get, but that's the way you interpret standard deviations. You're either using 2 or 3, and whether you use 2 or 3 is going to be solely dependent on what the shape looks like. All right, so that's a pretty good example. Let me do one more thing. What if I told you the exercise time of a student was, they said they exercised 30 hours per week? Would that be considered an outlier? And so what you'd want to do is calculate the z-score for 30 hours per week. This is one way of doing it. 30 minus the mean minus that 8 value. And again, it's 8.03, but that's going to be 22 divided by 6. And I'll do the real math here. Let's see. 30 minus 8.03. And I'm going to divide that by 6. I'm going to get a z-score of 3.662. That's an outlier. That falls more than 3 standard deviations above the mean. It's definitely an outlier. How about if someone said 15 hours per week? Well, 15 minus the mean divided by the standard deviation is going to be 1.16. That's not an outlier. How about if they said 22 hours per week? 22 minus the mean of 8.03 divided by 6. That's going to be 2.32. That's the tricky one, right? If you have an observer, a z-score of 1 point something, that's not an outlier. If you have a z-score of 3 point something, that is an outlier. The 2.32, again, you got to think back. We said we're using the modified empirical rule. We're going to judge that z-score versus a value of 2 because it falls. It's 2.33. That's the number I'm looking at on my calculator right now. And an exercise time of, 22, would be considered an outlier. So outliers, box plots, methods of detecting outliers, a whole bunch of stuff to look at here when we're describing data numerically. So hopefully that makes sense. If not, you know how to get hold of us. So long.